Okay, welcome this morning. And then again, first of all, who is ZoomAFM.com? And this is a platform that made of former employees of Agilent Technologies. We're all engineers and scientists, and we support the instrument of atomic force microscope made by Agilent Technologies. This here's me. Steve Raba is the service engineer. Shu Chan, he's not here today. Gerald Carter, application scientist. I still put Germany here. It's actually Austria. Yeah, we're Americans. We cannot tell the difference. Louis Pachenko is probably not here. He's busy. And while we are here, we try to keep your instrument running for 10 more years. And we want to support your AFMs, including molecular imaging, Agilent, and Keysight users. And we'll provide lectures and training. And we have business can handle your repair and maintenance. And I will actually personally provide on-site support. Okay, let me see, where is this? Yes, this is 3 websites here. OnQ is Steve's business front. Nanocue Technology is mine. And then we unite here in ZoomAFM.com every Tuesday morning. So this, I will just cover 15 minutes of the routine maintenance. And this is typically not a very interesting topic. However, when you start to make your AFM labs work, it becomes a lot of details becomes very important. For example, your installation of the AFM labs, how do you put things together? How do you do your maintenance, daily maintenance of a lab? And then how do you achieve everyday high resolution? There's many series of that. And then this is the first one that just say, when you have an instrument, how do you put it together? So the instrument that I have supported and a lot of other instruments normally are installed in a building, and these buildings from universities could be any kind, shape and size, could be any part of location of it. And then there are certain places that normally track a lot of noise and then instability and try to avoid. Give me example is that when your lab is close to underground parkings, or the lab has a very big floor, or it's close to elevators, close to machinings and activities. These are places typically have high noise level. Try to avoid that. And then this is a kind of table that describe it. How do you estimate your noise level to the certain decimal points? And for example here, typical home stereo volume is 80 dBs, and then record studio is 10 dB. It's very quiet, and so on and so forth. Kind of help you to estimate what is your noise level in a certain typical situation. And then in AFM, you try to install a system in a quietest possible, because the noise will kick into your imaging itself. This is a typical installation site of a Agilent Technologies AFM. Notice that the instrument is typically always on the left-hand side, and then your computer and screening is typically on your right-hand side. The reason is a very simple reason. You look at this door on the Pico IC, this door opened to the left. So if you put your computer on the left-hand side, this door will become a problem when you operate. If you really have to put your control computer on the left-hand side, I suggest you remove this door, or I suggest you basically put the door on the right-hand side. This is another kind of installation that to show you how do you install the system on an infrared microscope. This one, you have more freedom, because the access could be on both on right-hand side and next-hand side.
Remind me at 12 p.m.
This is a picture of this typical of operations. I like to have an L-shaped installation. Basically, you sit in one location, you can have your finger on the switches at the same time. You could operate the instrument, and then you have the instrument surrounded you. That's a good arrangement. Try to avoid these locations, doors, vacuum pump, vents, and then the fume hoods, which have a big draft of noise. And then these are typical things you need: the shelf, a big desktop, places you can put your sample, and then you need cleaning places, and then solvents, cleaning supplies to maintain a lab cleanness. The daily maintenance, I'm not going to read line by line. I show these things so that this presentation can be recorded, and then you can always go to our YouTube and then find these things, and you pause it, and you can write down these things on your lab notes or your lab things you could put on a wall. I'm not going to read it line by line. It's kind of boring. Okay. So maintain a cleanness is very key of maintaining a good AFM lab. These are the typical supplies. High purity water, that's very important. And then any water stored in a plastic bottle for a long time, they're no longer clean. And you need organic solvent, ethanol, acetone, methane to clean your tools. And these need to be stored in a chemistry lab. And you need to have gloves and, just regular stuff. Sulfuric acid, that's needed if you really want to clean your liquid cell, because you need to burn away all the organic contaminations using sulfuric acid. That's for extreme high clean requirement for example, electrochemistry. Substrate, you need to maintain a good supply of substrate, for example, graphite, HOPG, mica, glass slides, and then these steel sample dishes are very important. And double-sided tapes is a must, because that's how you fix some of the sample on the steel dish. And in the future, or some of the past presentations, I do mention that when you put a sample on the double-sided tape, you have to make sure that it is very firmly attached, because this is a big source of noise, or not noise, drift, because the softness of the tapes. Okay, I'm going to skip these. This is daily maintenance. How do you make a clean workspace? I have visited many labs, and then I would say this particular lab was 2 instruments installed on this very tight place. It's not the best arrangement, because look around, you cannot find places you can safely operate your scanner, and then doesn't have a big surface space to lay out your tools. You always need to have some kind of surface so you can work on. Always suggested. Daily maintenance, organize the bookkeeping, and this is very important, because imagine you image every day, you run a sample, you collect 100 images, and you kind of say, oh, this is a good image, and this and that, but after 3 weeks, you forgot what is everything about. Organization is very important. You have to keep your data well organized, as well as keep your book very well organized. And this will be covered in later presentations. There are a lot of techniques you can use. Daily maintenance, how do you have to maintain your calibration, open loop, closed loop, all these calibration. We'll touch base a bit more today by Steve on the calibration of the controller itself. And then there's certain kind of power on and power off sequence. This is a question always come up when I visit a customer and try to start them to use the instrument. There is certain power on, power off sequence you maintain. And again, I'm not going to read it line by line, and you can always go to the YouTube and then freeze the frame and read through them. How do you want to keep your laser on or machine on and off? I would say when you're not imaging for 10 minutes, you should withdraw the tip, because when you're not withdrawing, the high voltage is on. And when high voltage is on for a long time not scanning, it will gradually, slowly depolarize your scanner. So if you're not scanning, withdraw. If you're not scanning for an hour, you walk away a little bit, you should withdraw and then turn the laser off, because your laser has a finite lifespan. You should try to be try not to consume its lifetime when you're not using it. And we're not using it for a day, you could turn the controller off, and at the end, if the software crash, first you always manually withdraw by turning the knob counterclockwise to protect your tip. Then you reboot your controller. If you have to, you restart the software and computer and so on and so forth. Again, daily maintenance, mistake damages. I will not read line by line. You can always freeze the frame on the YouTube. And backup cleanup, and all these nice things. Okay, so that's about 12 minutes, 12 minutes. That's probably long enough. And again, before I stop, we'll mention Nanocue technology. There you can see a lot of my inventions of different kind of accessories, liquid cells, and then Nanocue Service LLC. It was the business name of Steve Raba, and he was the founder of this company, and he doing the repair. We also work with CSI Instrument. In the case that your instrument is too old, your computer is too old, your electronics too old, they actually build electronics that runs your Agilent AFM. It also runs other AFMs such as the old multimode from Vico, so it can keep your instrument running for a much longer time. And again, in the 30th of March, they will have a webinar and then basically describe their controller to run your old instruments using the new operation system. Okay, so I'm going to stop right here and then take some questions. At the same time, if you have any questions, unmute yourself and then you can ask me right now.
Hi, so I have a question.
Yes, go ahead.
Hi, this is Yuguan Kai from Texas A&M. When we operate the AFM, we have, as you show in your video, we have two black set-top box, right? Usually the LED panel display the deflection, the SAM signal, and the RFM. Right? In the meanwhile, on the software, right? Our software, you show a red dots, which show the position of the laser on the photodiode, and it's on the software screen. It's also display the RFM and the deflection and the SAM signal. Our case is sometimes this the like deflection and the RFM signal, the number on the set-top box and the number on the software on the screen is not the same. So I wonder which one I should believe, which one is the real number.
Steve, do you have comment?
Well, they definitely should not be different, right? So if there's a deviation between what you're seeing on the software and what you're seeing on the hardware is typically indicative of a problem with your system. So I would need to get a little bit more information from you to understand how much of a difference you're seeing.
We have two AFM. One AFM difference a little bit, roughly 0.3 volts in deflection to 0.5 volts in that value. Another AFM, the roughly difference always by about 5 times.
Okay, so that tells me that you probably have two different series of systems. There was one system that was produced years and years ago that had a 4.3 times gain in the head electronics box. So my recommendation is if you have that 4.3 times difference, you said it's roughly 5 times difference. That's probably because you have two different systems. They're two different revisions. Trust your software.
Okay, the software is okay. Yes. Okay, thank you.
Now, for the one that's only a few millivolts or, tens of millivolts, it's ideal that you came to this particular conference because this is where we're going to talk about why you have that difference. And that's all in your calibration of your controller.
I see. Okay, so basically your my take-home message for both systems, I should trust the software?
I trust the software, yeah.
Okay.
Based on the limited knowledge that I have of your particular operating setup, yes, I would trust the software.
Okay. Thank you.
Steve, when you say two different version revision, are you talking about the AC box or are you talking about the controller?
The head electronics box.
Head electronics box, I see. So one of them has a little calculation somewhere, right? That different.
Yeah, so the older head electronics boxes that were produced, I want to say somewhere around 2008 to 2010, those have a different algorithm in the summing signals inside the head electronics box. And there is a 4.3 X gain tied to those signals that newer version head electronics boxes don't have.
Interesting.
Yeah. In the newer electronics, you call the newer AFM. I noticed in the software, in the manual, there's an option which you can set the gains, so can somehow reduce the display on the software and make it match to the set-top box. Is that the proper way to adjust, or we just should leave the 4.3 times difference there?
My recommendation is leave the 4.3 times difference. Without doing a little bit more research, it would be hard to isolate exactly what you need to do to adjust that. So again, I would still lean towards the software values, the software readings, because that's what your controller is going to calculate everything on, is based on what the software is seeing.
I see. So later, for example, even for the amplitude, for example, if I want to based on if the amplitude in software show it's 7 volts, I want to calculate how much actually the amplitude, how many nanometers. I should use the numbers from the software rather than the set-top box.
Correct.
Okay, thank you.
Do you know which version of software you're running on each system?
Pico View 1.20.
Okay. Yeah, make sure that both systems are on 1.20.3. That's the most current version of software.
Okay. Okay, I see. Thank you.
Okay, while we're talking, I'm gonna switch the view to my computer running the AFM. And so we could have Steve take over and tell me what to do next. I'm gonna stop sharing here. And then switch Dell as a host.
I'll have to leave in about 15 minutes, and I have just a very quick question. And as we talked yesterday, because we have a lot of experts here, is there a good way of aligning the laser? Is there an easier way? Because each time when I tried during the changing the probe, I always have this trouble of take a long time to align the laser to the tip. Is there a better way of doing that?
I think if it takes a long time to do that, there may be something somewhere, I don't know, something wrong. Maybe the initial location or position of the laser spot is different, something like that. I would have to, probably you should set up a webcam and then zoom to the scanner itself and then do some adjustment. I want to see what's going on. If the laser spot is in the center of the view, what it's supposed to be, it should not take a lot of time.
Okay, is there an easier way to reset the laser spot to its like center? Yes,
you could take careful look from the side to the little top plate where the laser dial is plugged in. It's a plate. When you adjust the two knobs, you're basically tilting the plate back and forth and left and right. You're tilting it. So you could manually adjust it. So visually, you can see that plate is relatively parallel or flat. If it is tilted a lot, it's to a certain place in a position that it's stuck somewhere, that's probably indicated that your laser is very much tilted. And then the spot you see on the bottom is some kind of reflection. It is not what the laser is supposed to be.
So when you talk about the plate, is the plate vertical or the plate horizontal? How can I find the plate?
Okay, let me see if I can turn my camera to
Song, if I may. The
ahead.
ideal way for you to start out with your scanner is just look at the two adjustment screws that you use to position your laser and make sure that they're both vertical.
Mm-hmm. Yeah, that's what
if they're both
I'm
vertical,
trying,
that's your starting point.
Okay. because vertical, sometimes it's slightly tilted. And yesterday when I tried it, when they are vertical, then the laser spot is not it's not round. It seems like there is a slight odd shape there. That's why I'm having
Steve, I think maybe it was complete out of adjustment. That's what I think. I'm very close to her address, and maybe I should go take a look. Or she can set up a webcam and talk like this. This is the inside of the scanner. Okay, this is the plate. See that this thing that I'm tilting?
Yeah.
That's the plate. And this one is missing a ball bearings. You look at this, there's a ball bearing, should be right here. So it does not, it's right here. It's black, it's kind of hard to see. It should be here. It's missing a ball bearing. So when I let go, it's tilted a lot. And these two knobs basically tilt this thing back and forth. And just take a close look at this plate. This is the plate. This hole is where the laser is plugged in.
Yeah.
Just look at this top plate. And then this plate, if you look carefully, you adjust it so it is actually kind of parallel, kind of not, yes, see, this is a parallel, not this. This is like a tilted. See that? This is tilted. And that's, yeah, take a look at that one.
Okay, I'll do that.
Yeah.
Thank you.
And then also you did a video on how to align the laser, and that's on YouTube Song. So
Yes.
it might be a good idea to review that video as well.
I probably should set up a much better camera, much better lens and everything, lighting, everything next time. You know, before I even give a talk, I would just align the laser back and forth and then show you what I do. Because last time I used a webcam, which is not very good. There's not a lot of dynamic range. Next time I use a digital camera this way, yeah, next time I will show a much high quality of aligned laser part. That'll be next week. Yeah.
That will help tremendously.
Okay. All right, let me turn this share on again. Okay, let me adjust this a little bit. Okay, Steve, do you want to take over and tell me what to do?
Yeah, we can get started for sure.
Okay.
So right out the gate, we're going to have to take a couple steps back here. Your breakout box, is it plugged in to the front of your AFM controller?
It's not plugged in. That's why the instrument is actually running. So I have to stop the scanning.
Yeah, that's where I was going with that question. So if you're scanning, you're not going to be able to calibrate your controller.
Yeah.
So we definitely need to withdraw.
Let me remove the chat because this, I don't want to, yeah, okay. So let me go and then stop the scanning. Withdraw. So there's withdraw. And then do you want me to connect the 44 pin to the front of the controller, correct?
You're going to need to connect both the DB44 pin from the front of the controller to the breakout box and the DB9 high voltage cable to the side of the breakout box.
Okay, I'm going to step away from my computer and connect these two cables. Give me a second. And during the next minute, I cannot hear you because I'm taking off my headset.
So for those of you that are listening, it's important that you understand the breakout box needs to be connected directly to the front of the AFM controller. It should not be between the AC mode and head elect. It shouldn't be between the head elect and the microscope. It should be connected directly to the controller. while song continues to work, one thing I'd like to mention as well is while we do this with the standard breakout box, we will only have access to parts of the AFM controller. You will not have access to everything that I have access to with my signal access box. But that's okay. This will give you a rough idea of how to make sure that the rest of your system is properly operating.
Okay, I'm back. Now it's also connected to the breakout box.
Okay. My first and foremost step is always to check the power supplies before I do anything else, because if there's an issue with the power supplies, nothing else is really going to matter. So in the middle of the breakout box, there's 3 BNCs. One's labeled positive 5 volts, one's negative 15, and one's positive 15. So we want to go ahead and check those voltages and see where they're at. They should be pretty close to 5, 15, and negative 15. If there's a significant deviation, this is going to definitely cause problems with your operations.
Okay, so use the voltmeter and then go to DC voltage 20 volts. And now I have plus minus 15 volts. That's what I would measure, right?
Yes. And you can use the outside of any BNC on that breakout box to hold the black lead against so that you're not struggling with 2 hands on one BNC.
Yeah, it positive is reading positive 15.39.
Okay.
Negative reads negative 15.39.4.
And the 5 volt line?
4.96.
4.96. Okay. So they're not going to be 100% spot on every time that you do this, because you've got to factor in things like how well your DC multimeter is calibrated, right? That could cause deviations in your measurements. Just make sure that you're relatively close. And when I say relative, 4.9 is relatively close to 5. If you're at 4.3, you've probably got a problem.
I see.
With the 15 volt lines, they're a little high at 15.4, but the only adjustment that can be done to correct that is actually on the power supply itself. So you'd have to take apart your controller to get to it. And at honestly 0.4 volt deviation on that 15 volt line is not significant enough to worry about, as long as it's relatively close and they're relatively balanced. So the next step is to check your high voltage supplies. So what you're going to have to do is you're going to have to go to your software settings. Are you in front of the PC, Song?
Yes.
All right, so we're going to go to the scan tab under your servo controls.
Scan tab, yes.
And set your scan size to 0.1.
Scan size 0.1.
And then make sure that you're centered on your offsets.
Center.
And you can just click the plus button and that will automatically center it. And then activate your high voltage.
Activate. How do I do this? Normally I click approach.
So there's the little blue lightning bolt. You see the blue circle with the white lightning bolt next to your approach button.
There you go.
That will turn your high voltage on and off. So you'll notice that the green servo bar on the piezo turned green and the 2 scan buttons turned blue. That's how you know your high voltage has been activated.
Mm-hmm.
So now you're going to go to under servo control. You're going to go to the servo position tab. Up. Right there.
Yeah.
See how it says set Z position is checked. When we're doing our tests, we want to make sure that that's selected. And then you also want to make sure that you're at 0. So go ahead and select it and make sure that your position is at 0.
So this is you manually tell the DAC to output 0 on the Z, correct?
Correct. So right now, all of your settings, you're telling all of your DACs, all 5 of them, positive X, positive Y, negative Y, and Z to be at 0. So if you measure each of your BNCs on your breakout box, they should all be relatively close to 0. And you're going to hear me say relative a bit on this test, because relativity it's got a lot to do with your calibration files. So we're not looking for exact 0, but you'll want to measure all of your DACs, X, Y, and Z, and make sure they're all close to 0 volts.
Okay. So now I have a question. So when you measure that, you have this dip switch on the front. Should I switch the right out or switch the left in?
Honestly, my breakout box doesn't have switches. I have BNCs tied to everything. So I'm going to have to ask you to experiment and see which ones are operating properly.
My
I
understanding.
don't believe it
Yeah.
matters on the high voltage lines
Okay.
when you're doing this test, because it's really the switch, to my understanding, is just telling it whether or not to pass the signal through.
Okay. I think when you switched in, you are actually disconnect and inject the signal. So I'm going to switch everything to out, and then you have X plus, X minus, Z, Y plus, Y minus. I'm going to measure one at a time. So measure X plus, reading. Let me see. Should I put on 200 volts at range, right? You don't want to short the voltmeter.
My meters auto adjusts, so I don't typically look at that. But yeah, make sure that your range is appropriate.
I have a cheap meter and probably costs $10. X plus out, and both should read 0 minus X in and out. The out reads 1 volt.
1 volt is fine.
Yeah, it's actually fluctuate a little bit, 1 to 0.9, and Z out reads 0.3 volt, 0.2. Y plus out reads negative 3.1, and the minus Y reads 3.1 plus 3.1.
Okay, so that's relatively close to 0. And the reason why relative is important is because the reason that you're getting any voltage whatsoever has everything to do with your scanner calibration file. So if you change your scanner calibration file, those values will change. So don't stress, just know that you're centered in the power supply range. These power supplies go from 220 volts DC to negative 220 volts DC. So 3 volts is not something I would consider an issue at this point. We need to take more measurements. So what we're going to do is, if you go back to your servo control window for your Z position, and you look at where it says 0 nanometers,
Yes.
just type in some abnormally, obnoxiously high number. Just hit 99999, enter. What that's going to do is it's going to default it to the highest possible position. So if you go back to your Z out and you measure again, you should be somewhere around 220 volts DC.
Okay, I'm measuring Z out, and my range on my voltmeter is 1,000 volt, and I read minus 217 volts.
Yeah, so when you move in the positive direction, you'll get a negative value. When you move in the negative direction on position, you'll get a positive value. But you're almost 200 volts. And again, that has to do with your scanner calibration file. All I'm making sure is that your power supply turns on and moves to the proper direction with the proper amplitude.
Yes.
So now you can do the same thing with your servo Z position with an obnoxiously large negative value. And the difference that you'll see in your measurement is it's going to be relatively the same voltage, but it's going to switch polarity. Instead of it being a negative 220, now you're going to see positive 220.
Okay, I'm going to switch. I'm going to type in negative 9999, enter, and then measure the Z out.
Do bear in mind that this is 200 volts DC. It will shock and bite. So please be careful if you're taking these measurements.
Yes, I'm still talking. I assume I did it right. It's positive, reads positive 217 volts. So this is correct.
Perfect. So we know that the positive and negative power supplies in your controller are operating properly. You can go ahead and put your Z position back to 0 just for safety reasons. You don't want to accidentally shock yourself. And now we're going to do the same thing with the X and Y offsets. So with the X offset, put an obnoxiously high number for positive. Y offset, put an obnoxiously high number for positive as well.
Okay, X offset, I'm going to do 999. And then Y offset, go to 999. It's only 5 to 4 micron.
And that moves the position of those power supplies to their extreme on one side. So as you measure your negative X, you should get positive 200 volts.
Negative X reads positive 215 volts. And
positive X should read negative 215 volts.
Positive X reads and negative 215 volts. It actually output both on positive and negative. I thought you only go to one. I'm very ignorant on electronics designs. Let me measure the Y.
So Y should be the same thing. And as you're taking these measurements, Song, I'm going to keep talking. With your offsets in the positive extreme, your measured values will be opposite of the polarity on the box. And I'll say that again. If the offsets are set to the maximum positive extreme, and you look at your positive X output, it will be a negative voltage.
Yes, that's exactly what I measured. Correct.
Okay. So now all you've got to do is put a negative sign in front of the X offset and the Y offset to move it to the other extreme. So just an obnoxiously negative number.
Negative 10 on X offset and then negative 10 on Y offset. Let me measure again on the positive.
Now
X.
your polarities should match the BNC, right? If you're measuring positive X, you should see a positive 220 volts.
Positive is 212 volts and negative, measure X in negative 213 volts. Positive Y, 210 volts, and then negative Y is negative 210 volts, correct.
So all we're looking for here is that your power supplies move to the extremes as the software tells it to. So you go ahead and center it back and disengage your high voltage. And that's your basic high voltage test. That tells us that the system is working properly. If there was a problem with one of those high voltages, the polarity may not change, the value may not change. We're really just looking for change in the direction that we're expecting. So your power supplies are good to go. The next step is you're going to go ahead and click on your controls. And I'm sorry, your screen is kind of split at the top left. Can you slide that window over to the right a little?
Can you see it now?
There we go. So click on controls and we're going to go to advanced. And we're going to look at your inputs.
Inputs.
And right now, because you have nothing but a head electronics box plugged in, or the breakout box plugged in, all of these values should be 0. And the fact that you have some that are at 0.004, some at 0.012, that's a calibration issue in your controller. That just means that your controller calibration file is not calibrated. So everything should be relatively close to 0. So what you're going to do is you're going to open up your setup window, go to your controller, and see the controller calibration file that's selected right now. Is that the controller that you're currently using?
It is not, because I just switched cable from one to the other and then did not bother to do this.
Okay, do you have other controllers that you can select?
Can we just select one of these random like 3000 controller and
we can use the one you've got selected right now because you're going to know how to do this again. Yes. I just wanted to see if you had variables. Make sure that you're always selecting the controller calibration file that you want to calibrate.
I see.
And then you can move forward from there. It'd be a good idea, Song, for you to go ahead and take a screenshot real quick if you don't want to pause the video later, so that you have these numbers available so that you can reset your calibration file. But the first thing that we would do is we're going to set all of the offsets to 0 and all of the gains to 1.
All the offset input, right? Offset is 0?
On both input and output, you're going to set everything to a default 0, 1 setting.
I see. Okay. 0, 0, 0.
For your offsets, just do sample bias because we probably won't go through every single one of them.
Yes, it's not necessary. We just do one and the other will be, and then also the output, correct?
Yeah, just do the sample bias one. Don't worry about the rest of them. So sample bias, offset 0, gain 1.
Gain 1.
So this is our default starting point. If you look at your inputs, those values that are drifting again, you'll notice that they all line up to a calibration file parameter that you can adjust, right? So we're looking at servo at the very top. You've got negative 0.001, 002. It's kind of fluctuating between. Go to your offset in your setup window and just put in the opposite value of what you're seeing. So put in 0.0015. you've got a little bit more room to play with and it'll show. And notice, bam, right out the gate, you're back to 0.
I see.
That's
So
what
you
we're
add the
trying to
offset.
achieve on every one of these inputs. So go ahead and just put the opposite value in. And this is why the head electronics box will display a slightly different value than the software, because the head electronics box is taking the raw reading. The software is calibrating that reading based on this file and is displaying a slightly different reading than what the hardware is showing. If you recalibrate your inputs, that issue should go away on your system. And you literally do this for just every one of them on your inputs to bring them to 0.
I see.
If they're fluctuating 1 millivolt, that's not something that anybody's really got to stress about. That's just your DACs and tolerances.
I see. Okay. So you just type in to counter the offset on it and make sure they drop to 0.
And it's important to note that you do not have anything else plugged into the controller when you do this,
I see.
because it will throw off your readings.
Yeah, it's supposed to be 0 because there's no 0 input. There's 0 input basically. Yep, we could spend time on it. We can move on.
Yeah. So the next step would be to go to your controls drop-down dialog again. Advanced. This time we're going to look at your outputs. And we're only going to look at the sample bias output just for time saving at the moment. But if you go back to your breakout box, you have an output for sample bias. Right now, it should be reading 0 volts. What do you read on your multimeter?
Okay, I'm going to look at the sample bias, switch to out. Sample bias out. Let me go not 1,000 volt range, give it 2 volts range, or 20 volts in case we get it high.
To the 20 volt range, yeah.
Yeah, the reading, it's fluctuating a little bit. Let me push it hard a little bit on my fingers. Negative 0.12.
So again, you're going to put the opposite value into the sample bias offset and then measure it again. Now, when you're measuring your outputs, keep in mind that the offset that you put into the software is going to deviate a little bit from your multimeter, and you're going to have to fine tune it and dial it down to the specific 0 volt.
Yes, okay.
So where are you at now?
Right now, it's actually quite close to 0. It's actually on 0 right now.
It's on 0?
It's on 0, yes.
Okay, now on the raw outputs window dialog that you open from the advanced controls, set your sample bias to positive 5 volts.
Sample bias, 5 volts set.
Now let's see what the BNC is outputting.
Okay. Measure the out sample bias. 5.07.
So 5.07. I'm going to give you a speed trick on this one, but I'm going to give you the math first. The math is you take your known value, divide it by your measured value, and then multiply that by your current gain value for your new gain value.
I see.
So again, it's your known value divided by your measured value times your current gain. Well, we know that our gain is 1. Anything times 1 is itself, so we can eliminate part of our question here. Wrong side. You want to be on the sample bias.
No, sample bias, yes.
There you go. We also know that 5 divided by anything larger than 5 is less than 1, right? So put in 0.9.
That's the gain.
And see how far it came down.
I measured the sample bias again. It's measured 4.56.
So 0.9 is too low, 1 is too high. You can sit there and do the math if you want. It's not a problem. Or you can just do what you just did and find your medium, right? 0.95. Do I got to bring it up or down?
Yes, 4.8.
So we got to go up a little bit more.
Until you find the correct number. .92.
Can you put in 0.9823, please?
8.
If my memory is good, that's the number you started with.
It's 4.98.
So you can bring it up a little bit more until you dial it in until you get exactly 5 volts. Now, whether or not it's a true exact 5 volts, that's going to depend on how well your multimeter is calibrated more than anything else.
Yeah, now it's 5 volts. But I got the
All right,
point.
so now that we're at 5 volts, you want to go back to your sample bias output and you want to set it to negative 5 volts.
Sample bias output, negative 5 volts.
And then remeasure. And it should be negative 5 volts.
Here's it again. Negative 5 volts. Yeah, precise.
All right, sometimes you'll find that the positive 5 volts will read positive 5 volts and the negative 5 volts will read negative 4.99 volts. There'll be a slight imbalance. You can correct that with your offset. Don't mess with the gain. Use the offset to correct that. Once you've done the positive 5 and negative 5, you want to also output positive 10 volts and negative 10 volts and check both of those. What you'll find is it's probably going to be 10.01.
Let's try that. Positive 10 volts on the sample bias. Is it plus minus 10 volts is the limit, right?
Yes, that is the limit. So really all we're doing is we're making sure that you can get to those limits, but you're not going to be dead on 10 volts. It'll probably be slightly higher.
Yes, it's actually 10 volts, but the last digit kind of flick a little bit up and down.
And then check your
Otherwise,
negative
it's
10 as
pretty good.
well.
Negative 10 it is. It's negative 10.
Good.
And flick
And then just
on
for
and off
safety
with
reasons, go back
9.99.
to 0.
Back to 0. Got
Just
it.
so that we don't shock ourselves. Now, I don't know if anybody else noticed this while you were doing this. I'll just add this in real quick. If you change your sample bias, let's say if you go to 5 volts again on your sample bias, watch the deflection on your laser output.
All right, just put sample to negative 5.
You should see it move.
Yeah, it moved.
Notice the deflection is negative 5 volts.
Deflection, negative 5 volts. Yes, why is that?
Don't worry about the electronics. This is what is important. If you have the head electronics box that has the 4.3 gain in the circuit, you'll see a deviation of 4.3 between that deflection value and that sample bias value you put in.
Why is that?
So for the individual that had that issue earlier in the conversation, that's one way you can check it. Change your sample bias to 1 volt. And if your deflection goes to 4.3 volts, that's the version of head electronics box you have in your system. Last but not least, one of the things that you may or may not notice is all of the gains on your inputs are still set to 1. We didn't adjust any of the gains. That is your default calibration from the factory. The factory never adjusts these gains. If you are working with something like electrochemistry, it's important for you to understand how to adjust your gains as well, but you have to be able to do that on your own. You can simply do that by setting your 5 volt output on a calibrated output like a sample bias output and connecting a BNC cable from your sample bias to each of those inputs on your breakout box and see that they go to the proper value. And then you follow the same process on your gain. Take your known value, divide it by your measured value, multiply it by your gain value, and that will be your new gain for each of those outputs and inputs. And that's how you calibrate a controller. Of course, when we do this here at the facility, we've got access to every single one of these inputs and outputs that the standard breakout box simply doesn't have. And that's part of the value of the calibration done at the factory. But this will be enough to get you through any of your normal day-to-day activities.
Let's see.
So for the gentleman that asked about the head electronics box deviations, my recommendation is go through this process and make sure that you're calibrated and see if you've got any further issues from there.
And for our operations, basically, we just need to go through the calibration that we can, which is on the breakout box panel, correct? And then,
Yeah.
yeah, so if we want to do KFMs or electrochemistries and make sure the VEC, IEC are well calibrated using this method one at a time.
And normally I would remind everybody to go ahead and save the calibration file with a little save button next to the controller dropdown.
There you go. Yes. Mm-hmm.
But given that this is not the controller that you want to calibrate Song, I wouldn't recommend saving it. Just close the software and it won't save the changes. So you'll be back to where you were.
Okay.
If anybody's got any questions, that's all I've got to present.
See, yeah, go ahead and unmute and ask the question. Let me read the chats to see any questions. What is the dashed horizontal yellow line on the laser alignment? Oh, this question from Ben, and I think Ben, you're from Indiana University.
Yeah.
Yes. So what is the dashed line? Because this is right now we're set up at contact mode. This instrument does contact or tapping mode. When you do contact mode, typically you started the deflection at a negative value and you put a set point at 0. It's perfectly fine. You started at any value and put set point slightly higher. But as a reminder, when you see the yellow dotted line, as a reminder, your instrument software is at the contact mode. Okay, let me show you when it's not on contact mode. ACAFM. Okay, now the yellow dot line disappears. This is also a reminder that we're actually not on a contact mode, in AC mode. So when you see the dotted line, when you align your detector, your PSPD, you always align it so that red dot is slightly below the center line. When you go to contact, it goes to this. When you go to non-contact, this dotted line disappears. When you go to STM,
Song, can you set your sample bias to -1 real quick?
set sample bias to -1.
There, now you're aligned to your yellow line.
So it's actually at -1 volt. It's a reminder.
Yeah, so when you're doing contact mode, you want to make sure that you are at least below -1 on your deflection in contact. And that's what the yellow line's there for. It's to remind you that you need to be on or below that line for your contact mode to work properly.
Correct.
Okay, thank you.
Yes. Yep. Yeah. Because if it's not, if your set point is at 0, your red dot is above 0. When you click approach, the approach will immediately stop, and then the green bar turns red, and it tells you crashed. You did not crash. It's because your start deflection signal was not correct. Hope I answered this question.
Sorry to have interrupted, Song.
Oh, no interruption. You're supposed to.
Now you have a new trick. Now you have a new trick. You can use that sample bias to adjust your dot location.
Yeah, I don't know this thing exists before you tell me today. Yeah, go ahead.
I was going to say, it looked like Gerald might have had a question in chat.
No, I didn't. So this answered my question about the deflection, moving by changing the sample bias.
Yeah, it's a long, dirty explanation, but just know that if you're changing your sample bias, it's affecting your deflection.
No, cool. Thanks. It was really interesting.
Does it only happen this batch of head electronic box, or it happen everywhere?
Everywhere.
Okay. So you change sample bias and then you are changing the deflection.
At least in the raw outputs window, yes. But it's a good way to find out which version of head electronics you have too, because if you put 1 volt in sample bias and your deflection reads 1 volt, you have a 1-to-1 head electronics. If you put 1 volt in and it reads 4.3, then you have the gain factor in your head elect.
So when you change the sample bias now song in the main window, it would not change the deflection, right?
Well, we can demonstrate. Go ahead and zero out your
Whole window
sample bias.
you can control, right?
Okay, zero the sample bias. Down now what?
Go into
Open your
scan
EC.
control window.
Can I hear to both are talking? What do I open?
Scan and see controls.
Scan.
And here must be somewhere the sample bias, right? Is it in servo?
Servo, yes. Bias apply
okay,
to
here.
sample.
You cannot change it here. Okay.
Why I cannot change? Is it because it's not connected?
Open your EC control window. You can adjust sample bias in here, correct?
Can you try it? Yeah.
Sample bias, fixed tolerance, sample
Yeah,
bias.
go down. Yep, yes, here.
Right here, yeah, sample bias.
Mm-hmm.
What do you want me to do? Put
-1 or something. Yeah.
-1. Okay.
Did it change?
Yeah, it does change.
Interesting.
-2 changes. Yeah,
Interesting, huh?
Yeah.
I did not know.
Does this have an implication or an influence, when we do actual measurements in contact mode, for instance? Can we change
That
the sample bias?
that explained when I was doing an in situ imaging on a lithium battery and the deflection goes wild because it's the sample bias was changing during the experiment. Maybe that's the reason.
But is that true, Steve? You know that, right? Does it change the force actually then?
I honestly couldn't tell you the application's impact. I'm the hardware guy.
Yes, what happened is that when you change the sample, when you do an EC, when you're running a cycle of a thermogram, depends on what you set. You could ramping your sample bias up and down. And in one experiment, I see that I have to constantly adjust the laser to accommodate a big change, big drift on the deflection. Maybe this is the reason. It's not because of other things. I was wondering why the changing of my electrochemistry setting caused a huge shift of the deflection signal. I thought it's because of some electrochemical reaction is happening to the cantilever. Maybe what I'm observing is because of the changing of sample bias was coupled into the force.
Yeah, but that shouldn't be the case, this is an error, right? It should be
Probably
completely
yes.
independent, right? The sample bias and the force set point or the force.
Yeah, probably.
Well, if you change your sample bias, that could imply that you're trying to get closer to the surface. I don't know. I'd have to think through the electronics, to be honest.
Yeah,
I don't know why it does this. I really don't. I've never dug into it. I just know that it does this.
Okay. Well, this is good things to review.
Yeah, would
Let
be
me see.
to try the UFO's distance cycle and you change sample bias and see if it changes, right? This happen. Yeah. Would be interesting. Okay, good, sir.
So are there any other questions?
Yeah, Steve, I have just one here. This is Jason. I'm up in Canada here, still waiting for spring to arrive.
Yeah.
So I have like the old original Pico SPM and the controller was upgraded. So if I was to go through all of this and I'm running the Pico View 1.2.20.3, and I have a breakout box. So input side is going to be the exact same, but on my outputs, I'm going to have that for surely have the 4.3 gain. And I know I have that. So that's really, it's going to be the same way for me.
If I understand the question correctly, this is with the 4500 series Pico SPM, not the Pico
Yeah.
Plus.
Yeah.
I have not experimented with that system on this software, so I don't know. But I would imagine that it's the same. You're going to want to trust your software.
Yeah. I would just think, for sure on the output side, I'll see that 4.3 gain on there. So
Possibly, yeah. Yeah, I would expect it. I don't know. You said you've got a breakout box.
yeah, I guess.
Let me know when you try it out and let me know what you get, because it's been a long time since I've touched that system.
Yeah, and that controller was upgraded to the USB version and stuff. So that was around.
And you have a
2000.
DB25 breakout box, right?
Yes.
Yeah, give it a shot. Let us know how it turns out. That'd be interesting to find out.
Okay. Yeah, it'll be something for me to play with.
And just as a reminder, Jason, I still have a ton of stuff for 4500 scope. So if you need anything, let me know.
Do you have any scanners?
I do.
Oh, wow.
I have them too. I need to dig into my trash can and
Well,
yes,
mine look better than Song's do. Song's are in his trash can.
The
Yeah,
last
but-
one that I bought was about 2014 when I got a replacement. So it's been running since.
Yeah,
I
it's a
just
very nice
calibrate-
system.
I calibrated it a couple weeks ago. It still looks great. Luckily for me, over the years, as I broke scanners, we always kept the old ones. So I had extra laser diodes kicking around.
Yes, that's a good call.
So, but I think I might be on my last one or two of those, but with any hope, I've been talking with Song here and hopefully we'll be able
Oh yeah,
to.
yeah. I
buy
have
and
those. I will
upgrade it.
definitely find for you. No problem at all. Yes.
But I'm hoping to actually upgrade to at least the 5500.
That might be
Well,
something
good
we
luck
can help
with
you out
your-
with.
Yeah, good
Yeah.
luck with your funding things there. Last time we talked about, yeah. Yeah,
So-
you have to. Yeah. Do we have any more questions? It's already on top of the hour. If not, we see each other next week then.
Okay. All right, Song. Jason, reach out to Song and I. Let us know what your needs are. I'm sure we can find a way to help you out.
Okay.
Yeah, no, it's great. I was so happy that I found you guys doing this by chance. And, for us being kind of in the middle of nowhere, it's nice because we have a lot of old equipment here and,
Yeah.
it's at that point where we need, it's, one little break can cause it to die forever.
Well,
I love
fortunately, you
it.
have a very robust system, so
Yeah.
you got quite a bit of life left in that system.
Yeah.
I
But yeah,
love
anyways,
in the
thanks a
middle
lot,
of nowhere.
guys.
Thanks, Gerald, as well.
Thank you. Bye-bye.
Have a good day, everybody.
Everybody, bye. See you next week.
Thank you.
Bye.
Thank you, Song.